In this example, we are going to draw the Bode plot for the transfer function Ch equal to 20s over s plus 10, and this is actually a simple example just to learn how we can draw the or plot the different factors here, which are different components of our transfer function. Then we combine all the drawing into a single Bode plot. Okay, so you have 20s over s plus 10. Actually, this is the original transfer function. The first step we need to do, we need to convert or we need to change this transfer function into the standard form that we mentioned before in the term of j omega. Okay, so before we do that, we need also to make the simplification for the transfer function to have s plus 1 instead of we have a variables here or values in the either in the term of the pools or in the term of the zeros. We need to have the value of frequency over the value of the pool or the value of the zero. Okay, so what we need to do here, we are going to divide over 10. So if we divide this one over 10, it will give you 1. Divide this one over 10, it gives you 0.1 s or s over 10 actually. Then 20 over 10, it will be 2. So this is the first step of simplification. After that, we need to convert this one into the form of 2j omega over j omega over 10 plus 1. So now this will be the transfer function in the standard form in order to draw the frequency response or the Bode plot of this transfer function. So to plot this transfer function, we need to plot or represent each factor. So how many elements do we have here? Actually, we have only two elements. I mean three. We have three elements actually. The first element is the gain. The value of the gain after simplification becomes gain k equal to 2. The second is the derivative 0 or 0 at origin. So it is the value s here on the numerator represent the 0 at the origin or s equal to 0. So we call it the derivative factor. The third one is represent the first order pool. First order pool at the denominator here. So this is the first order pool. We have j omega over 10 plus 1. Okay. So that means we are going to draw three plots. We are going to draw three plots for the magnitude, three plots for the phase. Then we are going to combine the three plots of magnitude into a single plot for the function and the three plots of the phase into a single plot for the phase. Okay. So what we are going to do, the first we need to consider them one by one. So in the case of the factor here, we have the gain is equal to 2. So our magnitude will equal to, of the factor will be 20 log 2. So 20 log 2 here give you 6 dB. So the magnitude of our factor is 6 dB. That means when I draw it, it will be like one line or one straight line here at the point of 6 dB. Okay, so then after that we need to draw for the derivative factor or the 0 at origin or for the value of s here or j omega at the origin. So in order to find the magnitude here, it will be 20 log omega. So whatever is the value of omega here, so as we said before, it will be 20 dB per decade. It will be 20 dB per decade. This is the value based on the previous table that we see and our explanation when we find the log magnitude of the of the integral of the derivative or integral factors. It will be either 20 dB or negative 20 for the poles. Here we have 0, so it will be positive 20 dB per decade. So if we want to draw it, it will be like this one, 20 dB per decade. If we start from 0, for example, it will stop at 10 by 20 dB. If from 10 to 100, also it will be the same. It will be 10, 20 dB and so on. Okay, so it will be increment by 20 dB per decade. The first order, you can see here we focus first on the magnitude or log magnitude. Then we are going to draw for the phase. After that we combine all. So for the first order system here, or the first order bool, we said if you have a bool at the we need to consider 2 points for the 1 point for the magnitude, which is the point of the bool here. So at the bool here, which is P1, the point of the bool is at 10 actually, because we said omega j omega over 10, correct? Point 1 means j omega over 10. So at that point here, if omega less than 10, that means this is here less than 10, so it will be 0. More than 10, it will be 20 dB per decade. No, it will be negative 20 dB per decade because it's pool. In the case of 0, it will be positive 20, but in the case of pool, it will be negative 20 dB per decade. So before before 10 here, it will be 0, but after 10, it will be negative 20 dB per decade. Negative 20 dB per decade. Okay. So this is the three graphs will be like one, you have positive 20 dB, start from 0 point and forward, or from point 1 and forward. Then you have one is 6 dB and one will have negative 60 dB, 20 dB for starting from the point of 10, or the omega equal to 10. This is the drawing for, or the plot for the three components. This is for the factor, which is 6 dB. This is for the gain at k equal to 2. This one is for the 20 dB plus 20 dB per decade. This one is for the integral, derivative 0, or 0 at origin. Start from negative 20, for example, here, until 0, which is until this point, which is 0 here. Negative 20 to 0, we have 1 decade, 10 values from point 1 to 1. So it will be positive 20 dB per decade. From 0 to 10 here, from this point to this one, also another decade. So it will be also 20. So here it will be positive 20 dB per decade. Okay. So from 0, this is 0. Here is 20. Then after that, also for 100, also the same, it will continue with the same slope. You can see here we are talking about the slope of this line. The line slope is 20 dB per decade. The slope of the line is 20 dB per decade, which is positive. The third line here, we said we consider the value of the bool, which is 10. We said j omega over 10 plus 1. This will be the denominator of our transfer function. So the bool will be placed at the point of 10. So before 10 here, this is the point 10. As you can see here, this is the point 10. Before 10, all the values will equal to 0, because omega is less than omega 1 here. 10 here represents the omega 1 value. After 10, which is greater than omega 1, it will be negative 20 dB per decade. So it's negative 20 dB per decade. So it's true. So now we have these three plots for the log magnitude value for the three factors. If we want to draw the overall plot for the magnitude, we need to combine all these plots. So how to combine? We are going to add point by point. So for example, here we have negative 20, we have 0, we have positive 10, positive 6. So what is the result here? It will be shifted from negative 20 plus 6, it will be negative 14. So this line will go up until negative 14. So it will start from negative 14 and will go with the same slope, which is 20 dB per decade, until this point. After this point, until this point, because here the slope is 20. But after this point, I will remove this eraser. Okay, so if we want to combine all these three graphs or three plots into one plot, so we are going to add a point by point. So at the point of point 1 here, we have negative 20 dB for the first line. This one is 0 dB. That one is 6 dB for the gain. Okay. So if we add 6 plus 0, it will be 6, plus negative 20, it will be negative 14. So negative 14 will be at this point. Okay, so we are going to start from negative 14 instead of starting from negative 20. Why? Because we have shift by the gain of 6 dB here. Then from this point until we reach to here, there is no change until to this point here. Until this line, we only have 20 dB increment plus 20 dB. Just we are going to shape this one, draw line, I mean with the same slope of 20 dB per decade until we reach to this point. This point here, we have another component which come to the consideration here, which is the negative 20 dB per decade. So at this point, before it, only we have positive 20 dB, but after this point, we will have positive 20 dB come from the integral, I mean the derivative 0, and negative 20 dB come from the first order poles. So since you have positive 20 dB, negative 20 dB, the poles, I mean the slope at this point will be plus 20 minus 20, it will be 0. So the line will go straight without slope. When the line is straight, that means, or horizontal line, that means the slope is 0. There is no slope. Because we have positive 20, we have negative 20, we combine, so the result will be 0 slope. So the new plot for the overall system, for the magnitude response or magnitude Bode plot, will be like this one. Start from negative 14, go by 20 dB per decade, then go for straight line. So this is how the new magnitude log will looks like for this example. Actually start from negative 14, this is negative 14 dB, go by 20 dB per decade, then negative 20 plus positive 20, it will be 0 slope. It will be go horizontally here in horizontal. So this is for the Bode plot for the magnitude here. For the angle, it's also we need to draw for angle for each one is separately. So in the case for the angle here, we need to consider the angle for the gain is equal to 0. Then the angle for the angle for the gain is equal to 0. The angle of the integral 0 will be positive 90. Then we have the angle of the first order pool, and the angle of first order pool here we have 3 points of change. We have the point of I mean the point of the pool itself, then the point of the 10 value of the pool as we see here. So we can see from this table actually. This one we want to draw now. 1 plus j omega 1 over negative. So this is for magnitude. For the angle here, we have 2 points for change. We have omega 1 over 10, which is point omega 1. And we have the value of 10 omega 1 and after omega 1. Okay. So now in the case of our example here, the omega 1 here equal to 10. So our angle, if we want to draw the angle, the first for the gain, the angle is equal to 0. So it will be on this line, no change. The angle is equal to 0. Then for the derivative factor here, the angle is become positive 90. So it will come here, it will be positive 90 degree. Okay. But the angle for the derivative, I mean the first order pool here, the first order demonstrator pool, it has 3 positions actually before omega 1, I mean before omega 1 over 10. So for example, if this point is omega 1.10, omega 1 over 10, omega 1 over 10 here represent what? Actually omega 1 itself is equal to 10. So omega 1 over 10, it will be 1. So before 1 hertz, it has the value of 0. Then from 1 hertz to 10 omega 1. What is 10 omega 1 here? It will be 10 times omega 1, which is already 10 itself. So it will be until 100. That means before from 1 to 100 it will be negative 45. It will be like this one. This is 1 hertz, this is 100 hertz. This will be 45 degree or negative 45 degree per decade. Then after the 100 hertz it will be 90 degree negative. Okay, so this is how the change in the phase of the first order pool here. Then we combine point by point, like the same like we did before. From zero, this 90 stay continue 90 90 90 until here, until this point, which is 1 hertz. Then it will drop by 45 per decade, okay, until reach to the point of 10. Then it will go to the negative 90, positive 90, so it will go to 0. Okay, so as you can see here, the change, this table shows the change in the angle here for the omega from point 1 until go to infinity. So point 1 here will give you 90 degree, then at the infinity will give you 0 degree. This is the point of change. So in the figure here we can see we start, this is the overall change. It starts in the beginning here for the gain k is equal to 0. So 0 plus 90 still continue 90 90 90 until we reach to the value of the value of 1, which is omega 1 over 10. But omega 1 actually here is equal to 10, so it is 10 over 10. It will give you the value of 1. So at frequency 1 here, it will be dropped by 45 per decade. This is 45 degree, and for 1 decade, this is 1 decade actually. Then the second decade will be here. Also, it will be dropped by 45, continue 45 per decade, until reach to the 100. 100 represent the value of 10 omega 1. 10 omega 1 means 10 times 10, so it is 100. So we reach to 100. At 100 actually, the first order pool has angle of negative 90, and the first or the integral, or the derivative pool, the derivative 0 has positive 90. So we have positive 90, we have negative 90. The total will be 0. Now plus 90 minus 90, so it will be 0. So it will be lie on the line of 0 here. Okay, starting from 100 until infinity, it will be lie on the 10. So this is how the plot for the phase. The plot of the phase is like this one. Just come from starting from 90, because we have from 90 here for the 9. This one actually, this graph generated by using MATLAB. So that if you go for the origin, for that, if you want to make the approximation for this graph, so we start from 90, and which is at point 1 here, until 1. This is 1 point, so it will still go to 90 until 1. Then from 1 to 100, it will go with the drop of 45, negative 45 degree per decade. From 100 to this 100, from 100 to infinity will go to 0. So this is how the Bode plot for the phase, the Bode plot for the phase will be, for the overall system will be. Okay, so this is the for the phase. This one is for the magnitude. So we have two graphs, one for phase and one for magnitude. This is how to combine multiple plots into a single plot. So you are going to add point by point. Actually, they are more. This graph actually represent the overall graph or overall Bode plot. So the top part is using the magnitude. The lower part is for the phase. Log magnitude is on the top. Start from negative 14. Go up by 20 dB per decade until we reach to the value of omega 1. Then it goes for 0 slope. Then for this one also the same. It's go for this is point 1 here. This the point is 1. This the point is 100 here. After 100 is goes with the angle of 0, or as you can see here, the phase is 0 or the angle is 0. But this is more accurate because the drawing is using MATLAB, so it shows every change or every change, difference in the angle and every difference in the magnitude. While when we draw our own body plot by using hand or manual, we are going to approximate. So we are not going to see such curve here. So you can see this is the approximate one. The red color here represent the straight line, just straight line. There is no curve here. This is the approximate one, and this is one is the original curve. There are some other examples here. You can go through the slide, for example, more example on using or drawing the body plot. Our aim in this chapter will be after we can draw the body plot. So we are going to use this body plot into the representation or investigation of the system stability. So from this graph, we can identify is our system stable or our system unstable and so on. So next video will be more on the stability or identify the system stability based on the body plot graph.